terms of t is equal to 58t minus 0.83 t squared. What is A asking you for? The velocity at 1, right? So you're doing the limit as x goes to 1 of what?
As f of a plus h, or x plus
Well,
h,
we're just doing x.
oh.
There's two different forms, right? So let's do this one. If I go x to 1, what's the form have to be? F of x, so it's 58. Or actually, what? We can say t instead to make it consistent. T goes to 1. F 58 t minus 0.83 t squared, right? Minus what? Minus 58 minus 0.83. How did you get? Oh, you plug in 1 into that, right? All over what? T minus 1. Can you clean this up a little bit?
Yeah.
Yeah, that's going to be the limit as t goes to 1 of, let's put this in order here, negative 0.83 t squared plus 58t minus 57.17 all over what? T minus 1. Okay, let's just look at this for 1 second. What do you think? What is your immediate reaction when you see that limit? Okay, so your goal, what we've been doing, you're right. What we've been doing is we want to nuke that t minus 1 so we can cancel it out and actually plug it in. What kind of wall are you immediately seeing? Lots of terrible decimals. Essentially what you're being asked to do is factor something with a 4-digit number. Effectively, that's what you get when you have a 0.17 on the end of there. So are we teaching you how to factor 4-digit numbers? Is that something that you'd want to do by hand ever? No, absolutely not. So what could you do at this point? What could you do at this point? You could try polynomial long division, but I'm telling you specifically, this is something you do not want to do by hand. So what are you going to use? Calculator. Exactly. Zoom function would you use right now? Oh yeah, zoom, box. And we're a little bit past 1. Let's get a little closer. So I don't know, right there. Let's go up. And theoretically, what could we maybe see when we zoom in here? What might we see? Well, maybe. We hope not, because if there is, then the limit's broken. But if we zoom in far enough, what are we eventually going to see? You actually see a dot. You eventually get close enough that you'll see a dot. But if you trace this thing, let's just take a look. When we're going to x equals 1, right? It's a constant path. It looks pretty good. Keeps on going, getting closer, getting closer, getting closer. When x goes to 1, oh, I really zoomed in too close over there. Sorry. It looks like, so it's really close, went too far. About 56.34. 56.34, does that seem about right? That seems pretty good. Now, this is one way of verifying it, right? Another way of verifying it would be to look at a table, right? Remember tables? Look at tables of values. Oh, sorry. So we could, if we go back to our calculator here, we could do second table set, right? And let's start at, how about 0.99? And what should our delta table be? 0, 0, 1. You have to go 1 beyond. You can do 0.1. You just jump over it, right? So then you do second table, and what do we end up with here? It's getting closer, closer, closer. Should we see an error? Yeah. Absolutely. So we have a table, so you can use both. This kind of makes us feel better. The thing that's limiting, though, is that it should feel a little unsettling that we can't do this one by hand quite yet. But this does feel like there is an actual answer to this. Yeah, I mean, it really looks like we could zoom in even further, but right now, could we make a pretty good estimate of what's going on right here? Yeah, it's not bad. I mean, if you want to do it, it is what you get? Nice. So you can do polynomial long division, but again, if I gave you this kind of question on a test, what you'd really want to do is use these methods, because is it really easy to do the polynomial long division wrong on this?
Well, not really.
Oh, really? Oh, cool.
Three numbers.
Oh, not bad. Okay, well then, you know what? So it could be just as easy, but is it good that you know how to do it this way too?
Yes.
Yes. So what did you get for your exact answer?
56.34.
0.34? Cool. Nice. Nice. Very cool. Okay. And what are you eventually going to have to use on this? What do you think? Okay, what was f of x? Yeah, you're going to have to use long division. So what was f of x? It was 58 times what?
58 t.
So t, right? Yeah. Oh, and this is f of t, right? Because we got to be careful with, we're not using x, we're using time, right? Yeah. So it's 58t, yeah?
Minus 0.83 t squared.
3t squared, right? Good. 3t squared, right? Is that correct? And we're subtracting what? 58a minus a squared all over what? T minus a. So can we plug in a into t right now? No, because we'd end up with 0 in the denominator, which makes us really cranky because you'd have to divide by 0, and you don't like that. So now you need to find some way to factor the numerator, right? You have to find some way to factor that terrible numerator. What should you do first before you try to factor it?
Oh, set it up.
Yeah, clean it up a little bit. So it's t squared plus what? 58t minus 57 point... Oh, no, that's an a and an a squared, right?
Oh, yeah.
So, you know, I can just do this. Let's just leave it like this. 58a minus...
Can you get rid of that parentheses and do...
You could, but the reason I'm not is I really want you to think of those are just numbered. It's a static number. It's not a variable. So I like keeping it together. Yes, you could make it minus and then plus. You don't have to, though. So we really want to do this, though. T minus a into this thing, right? Now, you have to do that because do you see any way around that?
No.
At this point, what did we do before when we were doing this on our calculator, right?
Yeah.
We took this and we plugged it into our calculator. We got the limit, plugged it into our calculator, but now we can't. What's the key? What's the phrase?
Leading over leading.
You have negative 0.83 t squared over t. What's that going to turn into? Negative 0.83 t. Do you agree with that?
Yeah.
You multiply this out. Should you get the exact same thing right here? Yes. If you don't, you did something wrong. Minus what? TA, right? Negative 0.83 AT. Oh, it's positive. Thank you. Positive. And now we subtract it, correct? This goes away, meaning the first term, which it should, right? Leaving you with negative 0.83 AT plus 58T. You agree with that?
Yeah.
You have to be really careful at this point because remember, A is just what? A is just a number. What can you factor out of both of those terms? This is T times 58 minus 0.83A, correct?
Yeah.
The reason I'm doing that is now, this is the entire term, right?
Now,
So now you do this thing over T, and what do you put up top?
58 minus 0.83.
You get 58 minus 0.83A. Does everybody see that, everybody? This is just a number, right? That's like 7. So if you divide 7t by t, you end up with 7. So we're dividing that, and you end up with this. But now what do you have to do? You have to take this thing right here and multiply by both of those, right? So how many terms are you going to get?
4.
You're going to get 4 terms. You just have to be really careful about this. We can now just bring this down just to make it easier. It's what, 58a minus what?
No, it's not 58.
No, I'm bringing this down right here.
Oh, that.
58a minus 0.83 a squared. Let's multiply this out and just be really careful about it. Does everybody see what we're doing here? I'm going to write the new multiplication in green. Just make sure I'm recording here. If I multiply this thing in green, what do you end up with? 58t minus 58a, right?
Yep.
And then you get negative 0.83 at plus what? 0.83 a squared. When you subtract this, take a look, everybody. That cancels with this, right? Correct? And then you have negative 58a and negative 58a.
Well, that's positive. Yeah. So that's why.
Yeah, you got it, right?
Yeah.
This becomes, I'm sorry, yeah, the negative and negative, it still works, right? And then you have this, the AT, this right here cancels with that one, right? And this one cancels with?
No, it doesn't cancel.
Yeah, it does.
The one right underneath it.
Right.
No, it doesn't.
Minus and minus, subtract. It's really easy to miss it. And what do we end up with?
0. Yeah.
That right there is, phew. What you're terrified of is ending up with like 0.17. You're like, "Argh." So what's left? You now have, so basically you've figured out it's this. Limit as t goes to a of, what did we want in the denominator? It was what, t minus a? What's left? The factored form is negative 0.83t plus 58 minus 0.83a, right? All over what? Now what cancels? Yeah, this is gone, and you're left with the limit as t. It is crazy talk, huh? Negative 0.83t plus 58 minus 3a, right? Well, now yeah, we're not done yet with the limit. That we got there. So now we're plugging in a4t. So now you're left with negative 0.833a plus 58 minus 0.83a, right? So it's going to be negative 1.66a plus what? 58. Correct? So how can we check this with what we did in part A? What was the A? What we found the rate of change at 1, right?
Yeah.
What can we plug in right here? We can plug in any number we want, but let's just check this. Should this also work with 1?
Yeah.
It better. So if we did this, if we plug in 1, we get what? 58 minus what? 1.66. So what do you end up with? Is that exactly what we got before? Yeah, so did we just correlate this? Just because it works with one number doesn't mean it works with all of them, but is that a good sign? What it does show you, if you didn't get that number, 56.34, it means that this thing right here is wrong. Is this nasty? Yeah, it is. There's no way around it.
There
Yes.
is.
Of course there is, and if you ruin my punchline, I'll be really disappointed. Good. If you don't understand where it comes from, you can't use it in this class. We're going to get to the point where you can use some physics that many of you have learned, for example, and you can't use it at all. And the height is 0, right?
Yeah.
So 58, and I can't write, 58t minus, and I won't skip steps, minus 0.83 t squared equals 0, right? So 58t is equal to 3t squared. So that's equal when t is 0, so it's being fired from the ground,
Yeah.
which is great. But you're not interested in that. When does it hit the ground again? Not when it launched. So that's when 58 is equal to 0.83t. So t is equal to 58 divided by 0.83, which is, someone give that to me,
69.88.
0.88. So that's when it hits the ground. My guess is D asks you what's the velocity when it hits the ground, right? D says find the velocity when it hits the moon. So can you now find that? Yeah, because you know that the velocity function is 58 minus what? 1.66a. Oh, 1.66t. I'm just changing the name. It's fine. So if you want the velocity when it hits the ground, you know it hits the ground when the height is 0. The height is 0 at 69.88. So if you want the velocity when it hits the ground, you plug in 69.88. So we get 58, sorry, minus 1.66 times. Did anybody do this? What do you get? Negative what? Is it exactly negative 58? Wait, I'm confused.
Can you do 58 over what's the same?
So that's the velocity when it hits the ground. That's also equal to the velocity at 0. That's the velocity of the object when it fires up. Like, I mean, look at the function here. What's the velocity at 0? What's 0 times 1.66?
0.
It's 58. So the initial velocity is 58. The opposite, sorry. It's 58 going up, and when it hits the ground, what is it? 58 going down. Exactly, right. It's pretty cool. Pretty neat, huh? So if I throw a ball up, basically it means this. If I throw a ball up in the air at a certain velocity, what's its velocity when it hits the ground?
Same.
The same. What is the exception to that rule? There's certain things that come in play. If you drop something out of an airplane, what do you eventually hit?
The ground.
Terminal velocity, right? Yes, you eventually hit the ground. Correct.
What?
No, you're true. You're true. And as a side note, everybody, when you turn 18, jump out of a plane. Awesome, awesome, awesome. But the point is this. When you drop something out of a plane, what do you eventually hit? So here's the thing. If I launch something, are you capable of launching something faster than terminal velocity?
Yeah.
Absolutely. But if you launch something at terminal velocity with no added vector force on it, it's eventually going to start falling, and can it ever speed up to what it was launched at?
No.
No. But if you launch something less than terminal velocity, it will always hit the ground or come back to where it started at the same, it might not reach it, but it'll be the same as it launched from, right?
Yeah.
So you can't bypass. Why can't you bypass terminal velocity on Earth?
Gravity.
Nope.
No, the equilibrium is mechanically.
Equilibrium of what?
The normal force of the.
What?
Air resistance.
Air resistance. If
We're
there
not
was
denying
no
it.
resistance, would you ever slow down?
No.
No, you keep on speeding up. You need air resistance. So it's, and the cool thing is, this terminal velocity is for Earth, right? And theoretically, does terminal velocity change with regards to how high you are? Technically, but because gravitational force changes as you get further away from an object, right? But when you jump out of an airplane, you are so freaking close to Earth atmospherically that do you really feel the difference? No, you really don't. You really, really, really don't. But if you go really far away from Earth, this terminal, it changes. Do you understand what I'm saying, everybody? Right? So does terminal velocity change if you go to another planet? Absolutely.
Oh, I'm glad you told me that.
For you use the limit definition for instantaneous rate of change to find instantaneous rates of change at a specific value. So if I gave you a position function and I said, okay, this time, at this time, and at this time, find me the velocity to each one. What did you do first? You did 3 different limits, right? Right. What we've been doing for the past couple of days is generalizing it to, instead of evaluating each number, evaluating it for just A, and you do one limit, and then what does that allow you to do? It allows you to then take any time and find the velocity at any time, or any instantaneous rate of change given a certain function. That function, the function that you've been finding, the one with the A's in them, those are called derivatives. Limit definition look any different than what you've been looking at? No. We define the slope of the tangent line to a curve with this equation at that point. This is the slope, right? This right here, we also saw that the velocity of an object with position function s equals f of t at time t equals a is this. This is the one that you like in the back, right? Is there any difference between the two? No, they're just writing the same thing 2 different ways. Limits of this form come up all the time. We like to study rates of change all the time. Do we want to have to? It's becoming a realist. Nice. It's going to look like. It's going to look like this, like that, right? And then it becomes negative, really, 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 really negative, right? And then what happens right here? It gets less negative. So what do you know is happening right here? This is an interesting point to look at. It's getting really steep, and then at this point it starts getting, it's still negative, but it's less negative, right? So one thing you could do is you can just do, there's something interesting happening here. You know it's getting really negative, right? But then what happens? It goes back up again, right? Do you agree with that? So what happens here? It gets more steep, more steep, more steep. Oh, but then right here what happens? It gets less steep, but it has to be positive, right? So you know this thing goes up and then goes down, right? What happens here? Oh, it's just a little bit. But doesn't it get very steep here?
No.
No, so it might go down a little bit, but where's it going to change? Like right about there, so it goes, I don't know, like down and then up. And then what does this slope do? Can the derivative and the function intersect? Absolutely. Absolutely. Basically, can a point have the same y value as its slope? Yes, absolutely. So here's what it looks like. This is a rough sketch right here. Do we know anything really for certain? No. Did I give you a function for this green one? No. You can't. Question, yeah.
When you say like derivative,
Let's say we graph this right here. Y equals x squared. There's a neat function here. I'll just show you what this looks like. You ready? You go to math. It's 8 or 9. I can never remember. There it is, 8. And derive. You're taking the derivative, and you can ignore this right now because your formatting is not going to look like this.
Mine will.
Vars, what function are we deriving? The first one.
Y1.
And we're doing it at x. If we graph this, ready, zoom standard. What do we see first?
Our
Y
function.
equals x squared, and what should we see?
Bam, the derivative.
It's taking a little while because it's calculating each point. Is that pretty much what we just graphed?
That's so cool.
Absolutely.
All day, every day.
Absolutely.
Just give me y equals x squared every time.
You're all set, exactly.
Mix it up.
Mix it
Y
up.
equals negative
Okay,
x squared.
so the only thing I want you to do right now, actually, 1, stop talking. 2, have a general idea of where the visual connection between the two. The visual connection is right there. Look, wherever the slope is negative, the derivative is going to be below the x-axis. Wherever it's positive, and you literally just connect the dots. Sometimes it'll look overwhelming. I'll give you a crazy-looking function. I'll say sketch the derivative. Just look at the important points. Where is the derivative? 0. You are literally this semester, you're going to calculate where the derivative is 0 several hundred times in many different places. The derivative being 0 is a really important point. Think about it. It's when something turns around. It's when something hits its highest point, lowest point. Our optimization problem is kind of central to many areas of science. Absolutely. So if you can have a function that models the rate at which something is happening, You might want to know how to maximize profits, minimize losses, that kind of thing. It's all about where the derivative is 0. On any sort of big question, if you have no idea what to do and it's a calculus class, here's my joke. Take the derivative, set it equal to 0, and solve. You're going to literally do that 500 times this semester. 500 times, easily. Easily. Yeah, I know, it's tough, huh? A deal. Ready? I'll fix it for you. This is even on the record, too. You ready? This is on the record just for him. Ready? I'll fix it for you. I think I understand what he's saying. Ready? Watch this. This is how I fix stuff like that.
Yes.
Oh, that is.
Winner, winner, chicken dinner.
Did you make the box too big though? 'Cause it'll be weird.
Does that make you feel better?
Ah!
Oh,
Or worse?
Oh.
Here's what this says. This is huge. Listen. If f is
Big
differentiable at A, if you can find a derivative at A, the function is continuous at A. This is really important. When I asked you before, like, where is this function continuous? You know a function is continuous if it's made up of, like, logs and radicals on its domain, right? Do you remember that quiz question I gave you where I said, where is this function continuous? That was the same as asking, what is the domain of this function, right? Sometimes that's really hard to do. Another way to prove continuity is if you can find the derivative of a function at A, like if you know what the derivative is at a given value, you know that the function is continuous there. The key thing to realize is this. Derivatives imply continuity, but continuity does not imply the derivative exists. This is huge, and we'll talk about why later, but this is really important. Meaning, if it's differentiable, it'll be continuous there. But if it's continuous there, does it have to be differentiable? No. I just need you to remember that because I've said this before, and the backwards, no. No. We're going to talk about why later when you've done more sketching, and I think that's a great idea, Hannah. I'll do one to sketch.